I forgot to oops. But yeah. So can someone like give a proof for this? It's like super stupid, but just for the sake of formality. Okay. So positive into positive is positive, and negative into negative is positive. And since we're multiplying x by x, so both the numbers have the same sign, so it has to be positive or zero in case it's 0 into 0. But something more interesting could be if x squared is greater or equal to 0, can you imply that x is real? That's slightly less trivial, but probably not that hard. If you have an idea, just speak up. Even if it's wrong, it's fine. Anyone?
I think it must be real.
Mhm. You have a reason to believe so? Or some sort of intuition? Okay, let's say it's A plus IB belong to reals, and I is square root of -1. Well, if x is real, we must prove that b is 0. So if you square this thing, you get a square minus b square plus 2ab iota greater or equal to 0. Can you draw something from here?
Can we say that as the comparison of complex numbers is not possible, the imaginary term over here must be zero, hence like one of those is zero, but it can't be a, else it will be negative.
Yeah, so basically that. So if 2ab is not 0, so that means you're comparing a complex number and 0, and you're saying a complex number is more than 0. Well, that may sound logical at some point, but complex number is basically a point on this real imaginary plane, and you can't really compare 2 points, right? I mean, you could think of this point to be smaller than this point or this point because the distance is less, but there's no like formal way of comparing 2 points on a plane. So 2ab must be equal to 0 because there's no way you can compare two complex numbers unless they're real. That also gives us like a sort of like a intuition sort of a thing that when in a problem you're given that let AI let all AIs be greater than 0. And you instantly know they're reals, even though it's like a given sort of a thing. It's just like you should remind yourself that they're reals. You can apply all sort of things. Now, since you know that 2ab is 0, you can imply that ab is 0. So if b is equal to 0, we know that x is real. But if b is not 0, then a must be 0. What can you conclude from that?
Then the inequality does not hold.
Exactly. Because you get 0 squared minus b squared plus 0 is greater or equal to 0. That means b squared is less than or equal to 0, where b is real. But that is not true. We know that that's not true. Implies a can not be 0 unless B is 0. So we get that this inequality is like a two-way thing. It may seem like sort of useless at first, but it's really not. We could do some great things with it. Um, let's see a stupid problem though. If x raised to 5 plus ax raised to 4 plus bx cubed plus cx squared plus dx plus a is 0. And if you're given that 2a squared is less than 5b, prove that all roots can not be real. I guess you can try it for a couple of minutes and we'll discuss it in a bit. Also, let me know if the previous part was not clear. I think I went a little too fast. Okay, so we know that the Vieta formula thing gives us that my negative of a is the sum of all roots, and the third coefficient basically b is the product of all roots taken two at a time. And if we square the first equation, we get that a squared is summation of squares of, sorry. Okay, so squaring this thing gives us a square is summation ri square plus 2 summation ri rj, which is summation ri square plus 2d. And twice of a square is just 2 summation ri square plus 4b. If 2a square is less than 5b, then that gives us b is greater than 2 summation ri square. And this is summation ri rj. Essentially, you have 2 summation ri square minus summation ri rj is less than 0. Uh, what can you conclude from that? This Okay.
Would it be a good idea to explain Vietas? Some people don't know Vietas.
Okay. Okay, so Vietas is not nothing really special. How do you spell Vietas? Okay, I. So if a polynomial can be written as x minus r1, x minus r2, x minus r3, x minus rn, and roots. And there must be some leading coefficient, let's call it C. And then, okay, let's not call it C. Let's call it AN. Then we could also write this polynomial in this form. Because if you multiply all the terms, you get like a sequence of coefficients for each power of x. Clearly, you can see the coefficient of x raised to n must be an. Kind of predict what the coefficient of x raised to n minus 1 will be. So when you say coefficient of x raised to n minus 1, that means you're multiplying the term x n minus 1 times. And the last time you're just choosing a constant. So it will be like x raised to n minus 1 times one time we chose minus rn, one time we chose minus rn minus 1 time, and then one time we chose negative r2, one time we chose negative r. And there's also this leading coefficient. So there's always an here. So this coefficient will be nothing but an into, let's take the negative outside, r1 plus r2 plus r3 plus rn minus 1 plus rn. So that gives us the second coefficient is just divided by the first coefficient. So let's call this an minus 1. So an minus 1 by an. If we take negative of that, we get summation of all the roots. And if you look at this coefficient, the third coefficient, it's not that hard to see. You should try proving it yourself. But an minus 2 by an gives you product of all roots taken 2 at a time. And you could extend it to all the coefficients because this will be summation of roots taken n minus 1 at a time. And this will just be the product of all roots times an times an and minus 1 raised to something.
For the original problem, I gotta prove without Vieta's formula. So, if a function has all of its roots real, then I don't remember the name of the theorem, but by some theorem, then if you differentiate it, all of its roots are still real. So, you differentiate it thrice, and but you know that 2a squared is less than 5b, so you get its determinant is less than 0, which is a contradiction.
Okay, that's one way to do it. Differentiating thrice, that probably works. But the point was to get this thing. And from here to say that Ri minus Rj is raised to 2. I'm not sure if it's correct. Let me just check this once. It seems correct. What does this like expanding this? What does that give you? By this I mean like alpha r1 minus r2 raised to 2 plus r1 minus r3 raised to 2 plus r1 minus r4 raised to 2 r1 minus r5 raised to 2 and so on. So this equation is nothing but 4r1 square, 4r2 square, 4r3 square, 4r5 square plus, sorry, negative 2. If you take that common, it's r1 r2 plus r1 r3 plus r1 r4 plus r2 r3 r1 r5 and so on, which is basically 4 summation ai square minus 2b. And since it's a sum of a bunch of squares, it must be greater equal 0. So that gives summation not ai, ri square is greater than b, greater equal b, which is the opposite of what we have. We have this. So that means all roots cannot be real. I think that was fast, but yeah, I hope that's clear. You should try working this out on your own, especially if you just saw what we are tasking. Is that okay? Okay. Now, I think uh, let's move on to something slightly more complex. Let's do Cauchy's inequality. What does the inequality even state? So it states that if A1, A2, A3 till An are n reals and B1, B2, Bn are n reals as well, then A1 square plus A2 square up till An square into B1 square plus B2 square up till Bn square. This summation is greater equal summation ai bi raised to. I think that's the thing. And also fine. Yes. So I'll give you a couple of minutes to try because it's slightly hard, but not too hard. Give me a second, I'll be back. Oh, I am really not sure about what inequalities are acceptable in a RM and which are not. Because back when I wrote RMO, inequalities was not even a part of the syllabus. Like maybe it was the part of the official syllabus, but it really didn't ever show up. So I am really not sure. But I could get back to you. Yeah, the AMGM is probably like the most organized way. Okay, not most, but one of the most organized ways to prove that. So, uh, someone recommended using EMGM after expanding. So let's see what we get after expanding. We get A1 square B1 square plus A1 square B2 square plus A1 square B3 square up to A1 square Bn square. Then A2 square B1 square plus then we get an square B1 square plus an square B2 square up to an square Bn square. This is the left hand side. Um, what happened?
Hang on. Do people know AMGM?
Yes.
Yes.
Okay. Is there anybody who doesn't know AMGM? Like, it's completely fine to say yes, but you can raise your hand or do a thumbs up or something.
That is fine too. I will go over a very nice non-AMGM solution. Let's just do this one because it is a good proof. In the RHS, we get A1 square B1 square plus A2 square B2 square an square Bn square plus 2 A1 A2 B1 B2 plus A1 A3 B1 B3 A1 AN B1 BN plus A2 A3 B2 B3 A2 A4 B2 a lot of stuff. You can easily see that this term, this and this diagonal sort of a thing, they got cancelled. And then using AMGM on terms like, if you look at this term, then this is A1, B2, B1, A2. So if you use this diagonal, then this is greater equal to A1, A2, B1, B2. And then this term is this thing. And then this thing would be this diagonal. And it's basically like a thing that is not how big the mattress is. You keep working through pairs and it would eventually work out. Is that the AMGM you were working on? Or is that a cleaner way? Yeah, I don't think there's like a significantly cleaner way. Using AMGM at least after experimenting. There's another proof which I personally quite like. So all we've learned till now is this
The
inequality.
voice is not
Oh, I'm sorry. Let me see.
Oh, it's clear, it's clear. I think it might be a connection issue at your end, Lavish.
sorry.
So all we have essentially learned till now is the triple inequality. That if something is real, then its square is positive or zero. So let's look at this expression. A1x plus B1 raised to 2, which is obviously positive. A2x plus B2 raised to 2. Again, greater equals. If we add all of these, we get A1x plus, sorry, we know that their sum is also greater equal 0. But what do we actually get after adding them? So each equation is essentially just ai squared x squared plus bi squared plus 2ai bi x greater equal 0. If you sum all of these, you get x, you get a quadratic basically next. And the coefficient for the first term is a1 square plus a2 square till an square plus x times 2a1 b1 plus 2a2 b2 plus 2a3 b3 2an bn plus b1 square plus b2 square b3 square up till bn square. Now, for a quadratic equation to be always above the x-axis or lie on the x-axis,
The discriminant should be negative.
exactly. What is the discriminant here? It's, let's call this term x, y, and z. So discriminant is y square minus 4xc less than 0.
Why here less than 0? Shouldn't it be less than equal to?
Oh yeah, y square is basically 2a1 b1 plus 2a2 b2 2an bn raised to 2 less than equal 4 times summation ai square summation bi square. If you take the 2 out of the bracket, you get 4 summation AI BI raised to 2 less than equal 4 summation AI square summation BI square. And we've proved it. Is this okay? Can someone help me figure out the quality case here? Exactly. So since we summed up a lot of squares, and for the equality, the discriminant should be 0. And when is the discriminant 0? In a quadratic. When it has like a double root. What does that imply? Probably not the best way to explain it. Uh, I can't see. Okay, but we know this quadratic has a double root. Oh, the discriminant is 0 because for the equality case, this thing holds this thing holds equality. This thing holds equality. That means this thing holds equality. That means y square is 4xz. That means the discriminant, that is 0. I am not able to scroll. Okay, let's wait for a couple of minutes. Till then, people can think about what does discriminant equal 0 imply for the value of x. Not for the value of x, for AIs and BIs. Yeah, so notice this point. Let's call this alpha. For x equals alpha, this quadratic equation is 0. That means the sums of all these squares which form that quadratic equation, that is 0. That means each of those small brackets that have to be 0 because we're adding a bunch of non-negative terms and they sum up to 0. That means all the terms are 0. That implies AI x plus bi raised to 2 is 0 for all I, not x alpha. Imply bi by ai is negative alpha, which has to be constant. So the value ai by bi, that is fixed. So the equality case is when AI equals bi into some constant c for all I. Is that okay?
Yes.
But there's also this thing that here we assumed that the quadratic that is formed that does not have a leading coefficient 0. Like in the sense that we assume that sums of all the AIs are not 0. That means like not sums of AIs, but summation AI square is not 0. In case it was 0, the equality still holds. We just get that all the AIs are 0. So equality is this, or AI equals 0 for all I slash BI equals 0 for all I. Well, yeah, you could say C equals 0. Yeah, that just includes it.
Can you please repeat how we get the equality when summation of a square is equals to 0?
Okay, so did you follow till the point where we said discriminant has to be 0?
Yeah.
So since the discriminant is 0, that means we can say the quadratic has a double root. Like the graph is something like this.
Yeah.
And let's say the root is alpha. So at x equals alpha, this quadratic, the value of this quadratic is 0. And this quadratic is basically sum of a bunch of non-negative terms, these non-negative terms. And if you're adding a bunch of non-negative terms and you're getting 0, that means each of the negative term has to be 0. Like a1 alpha plus b1 square has to be 0. a2 alpha plus b2 square has to be 0. And if the square of something is 0, then we know that the term ai alpha plus bi, that is 0. That gives us minus alpha is bi by ai. So ai is bi times some constant for all I.
Yeah.
The other thing I think Shreya pointed it out, the only like edge case I had to see was we assume that summation of ai square is not 0. Otherwise, it's not even a quadratic, it's like a linear equation. But as Shreya pointed it out, in that case, the equality still holds and C is just 0. So we don't have to deal with it separately.
Okay. Okay.
I think we can like I'm not sure. Like I know there are like a lot of proofs with like dot product and cross product type things, but I don't want to get into that right now. I just wanted to show the trivial inequality uses. So maybe we'll skip the rest of the proofs for now. Let's look at this problem.
I have one question.
Go on.
We got C equal to 0 case, but when are we assuming that the BI are not all 0?
Well, are we not assuming BIs? No, we're not assuming BIs are not all 0. They could very well be all 0. And the quality good.
But then AI is equal to, BI once AI is fixed doesn't make much sense. Like it's trivial. Is that it?
Okay, so I think you mean that if we fix AI and let's say some A1, like I'm not sure if that's what you mean, just clarifying, but if some 8P, let's say 0, then
Okay,
we,
never mind. I got it. Yes, because
yeah, this is
like
not,
I was worried about the case when BI is equal to 0 because then fixing AI would be difficult. But I think like you would get BI is equal to minus alpha times A, which pretty much fixes.
I didn't get that, but if the doubt is clear, I'll not get into it too much. Let's look at this problem. Let A1, A2, A3, AN, and B1, B2, B3, till BN be true and real numbers. Such, oh, sorry, positive. Such that A1 plus A2 plus A3 up till AN is B1 plus B2 plus B3 up till BN. Prove that you can try it for a few minutes and then we can go over the proof. You could do that. Yeah. Is the problem clear to everyone? T2 is just one. I'm not sure if everyone knows what T2 is, so let's see. Let's see. This is what we have from the Cauchy's inequality. And we hope to get something like this. Does anyone have any ideas on what could be your squares and the other sum of squares?
Like here with the LHS, we can just take A1 plus B1 plus A2 plus B2, like these brackets, and then by like Cauchy-Schwarz, we will get A1 A2 till an squared on the other side, and then send that to the denominator and it.
Let me just write it down. And the other thing is A1 by root A1 plus B1 raised to 2. Is this what you meant? If
Yes, yes, yes.
you know by Cauchy-Schwarz, this is greater equal. What do we get after we multiply these two? Like this is, so we get A1 plus A2 up to an raised to 2. That implies A1 squared by A1 plus B1 plus A2 squared by A2 plus B2 up till an squared by an plus Bn is greater equal A1 plus A2 up till an raised to 2 upon A1 plus B1 plus A2 plus B2 up till an plus Bn. Can you tell me what the right hand side becomes after simplification?
Since A1 summation of AI is equals to summation of BI, so we get the desired inequality.
And that is what we had to prove. We could use the similar idea to prove the T2's inequality. Or Cauchy inequality and Angel form, which just states that AI squared by BI plus A1 squared plus A1 squared by B1 by A2 squared by B2 up to AN squared by BN is greater equal summation AI squared over summation BI. Can you try proving this? Where AI well, this is again the same idea. Is that okay?
Yes.
That's good. Let's move to something slightly different. Induction. I'll just sort of explain what induction is. So let's say you have to prove that 1 plus 2 plus 3 up to n is n into n plus 1 by 2. It's like a very famous thing. Well, I know that. Let's call this equation P of n. I know that P of 1 is true because 1 equals 1 into 2 by 2. Now, if I can prove a statement, if Pi is true, implying Pi plus 1 is true. If I'm able to prove this, then I'm saying that the statement Pn is true for all n. Let's see how that works. Let's say I managed to prove this somehow. Then I know that since P1 is true, P2 is true. Now we know P2 is true, so P3 is true, and we can just go on with that. So essentially that if you have to prove a statement for some number, for like all integers or all positive integers, something like that, and you know that it's true for some small case, then you're essentially left with such a claim, which seems much easier to prove now that you have information about the number prior to the number you have to prove for, instead of like jumping into this big thing with basically no clue. Well, this is sort of easy, like I'm sure everyone has seen this. But if you know this is I into I plus 1 by 2, and if I add I plus 1 to it, then the LHS becomes 1 plus 2 plus 3 up to I plus 1, and RHS becomes I plus 1 by 2, I plus 2, I plus 1 into I plus 2 by 2, which is this thing. So I've basically proved the claim, and now I know that this is true for all n. Like, just, I'm not sure if this is the right way to say it, but it's basically how the domino thingy works. Like when you push one domino and everything falls down. That is basically what induction is. If that is clear, we could try proving this inequality.
I have a question.
Yeah, go on.
Here we were just proving for the naturals. If like hypothetically we had to do it for the reals, and I know that it is true for Pi, and I like show it for I plus 0, like I plus 0 plus like a number that is infinitesimally small. So will that also work?
Well, with reals, the problem becomes that in naturals, it's very like easy to see what the next upcoming number is. Like if
Yes, that
starting
yes,
with
yes, that
10,
is.
then 11 is next.
Hmm.
But in reals, like if you're starting with 10, the next, you really don't know what that is. And
Yes, so that is why I replaced one with like x as limit of x approaches 0 from the right. Does that work? Or
I I'm not sure about that. I don't think that should work because like it could work in some circumstances. I'm really not sure. I haven't looked into that. But with reals, there are a lot of other ways to go for it. Like you could always work with situations like assuming X lies
yes,
between.
yes, yes. There are ways. I was just curious.
Yeah, like you could work with like the range of X and induct on the range of X and just assuming something is real and inducting on that. something is natural and inducting on that particular number. Like you could induct on the floor function of x, or yeah, you
Yes.
can
Okay.
get. Let's try proving this. It basically says that if x equals 0 and n belongs to naturals, then 1 plus x raised to n is greater or equal 1 plus xn. Yeah, that is
And you just do binomials theorem.
what?
And you just use the binomials theorem.
I'm not sure if you're saying binomial or Bernoulli's.
No, binomial.
You could try that.
Because then that makes the problem trivial.
Does it?
Because if you expand 1 plus x to the power n, you get 1 plus nx plus a bunch of other terms.
Oh yeah, makes sense. So by binomial, this is 1 plus x times n plus x squared times n choose 2. Da, 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 da. And this is obviously greater than 1 plus x. That is what you're trying to say. Well, yeah, that is okay. Let's think of induction for a while.
Through this binomial, how can we show equality?
Well,
N
the
equals 1.
mm, I'm not sure the equality holds for most cases, because if you just take n greater equal to, it's a strict inequality. Yeah. Equality only holds if n is 1, and that just holds for all x. You can actually prove that for n greater equal to, it's a strict inequality. Let's try. For n equals 1, it's clear. 1 plus x greater equal 1 plus x. Say for k equals for k equals I, 1 plus x raised to k is greater equal 1 plus x into k. Now let's try for k equals I plus 1. 1 plus x raised to I plus 1 is just 1 plus x raised to I into 1 plus x, which we know is greater equal 1 plus x into 1 plus xi. This is 1 plus xi plus x square I, which is 1 plus x into I plus 1 plus a perfect square times a positive integer. That is obviously greater equal 1 plus x into I plus 1. Now, if x is not 0, which we know x is not 0, then anytime I is greater than like 0, like I is 1 or whatever, then this inequality is strict. So since I is like, if I is greater equal 1, that means I plus 1 is greater equal 2. So for any n greater equal 2, the inequality is strict. And for n equals 1, it's like an all-time equality. So but otherwise, yeah.
By strict, you mean that it is always greater than and not equal.
Yeah, it's never equal. Well, this is like not the complete Bernoulli's inequality, because in that you don't have n as belonging to naturals, you just have the units. And x has condition, I think, -1 instead of 0. But I think that's slightly harder to prove. If you want, you can prove it later and possibly try some problems using that. I would recommend India PST 2022 P1. But yeah, we don't have to go into that right now. What we could try is this problem.
The
Let me,
question you are going to show is from and that uh, team selection test.
no, you could try this later. I'm going to show some APMO problem. I think 1999 P2. This says that A1, A2, A3 up till whatever be a sequence of real numbers satisfying AI plus J less than equal AI plus HI for all I comma J. Possible. A1 by 1 plus A2 by 1 plus A3 by 3. AN by N is greater equal AN and naturals. Let's try this one.
Can I and j here be equal to?
Yeah, they can be. Like you can say A2 is less than equal to A1.
Less than equal to A1 or twice of A1?
Twice of it.
I have done this before. Could you give me another?
Oh, you want a new problem? Mm, let's see. Do you know the proof for rearrangements inequality?
Yes.
Just give me a second. You can. Okay. How about you try this? Try this. I was told some people are done with the other one. So, yes, okay. Give me a second. You can try the fifth one. If you're done with the rest, but you don't have to. Actually, let's just discuss the first one.
What's on line 2? It says M is something 1.
What? Oh, that means M is not one.
Oh, not.
Let's try induction naturally, because yeah, for n equals 1, it's just a1 by 1 greater equal a1, which we know is true. It's not necessarily for this step of induction, but just to get a feel of how things are moving, let's try for n equals 2. a1 by 1 plus a2 by 2. We need to prove this is greater equal a2. Oh, it's just same as proving. a1 by 1 is greater equal a2 by 2. Just same as 2a1 greater equal a2, which we know is true using ai plus aj greater equal ai plus j. Now, let's say a1 by 1 plus a2 by 2, a3 by 3, ak by k is greater equal ak. And to prove a1 by 1 plus a2 by 2 equal ak plus 1 by k plus 1 is greater equal ak plus 1. That is what we have to prove. And if we are able to prove that, we would be done. Is that okay?
Yeah.
Can you, okay. Let's define pi as ai by I. We know summation bi is greater equal ai, not ai, ak. I is from 1 to k. And well, I should have introduced. Okay, so going back to what induction was, there's also a thing called strong induction. It's basically the same thing, except that instead of assuming if pi is true, we assume pi is true for, like, px is true for all I less than, for all x less than equal I. That does not change the dynamics of the induction, because you're still like, if it's true for 1, then it's true for 2, because it's true for all numbers less than 2. And since it's true for all numbers less than 3, because it's true for 1 and 2 now, it's true for 3 as well. And now, since it's true for all numbers less than 4, it's true for 4. So here we can assume that px is true for all x less than equal I. Is that clear to everyone what strong induction is and how it's basically better than induction, even though they're the same?
Yeah, it's clear, but I also sometimes get confused whether to use strong induction or induction, like which will be more helpful.
Just use strong induction because you have more information and the two things don't really differ by anything. Like the dynamics are still the same and you're able to assume a lot more information about your problem in strong induction instead of just normal plain induction. Like you're not losing anything. Okay, back to this. So it's less than equal and we just prove this for m plus 1. Is this fine?
Yeah, yeah.
Now, if we look at if we add like bk plus 1 to it, and okay, what am I doing? If we look at this thing, summation bi, I goes from 1 to m plus b of m plus 1. That is nothing but b1 plus b2 plus b3 up till bm plus bm plus 1. And we have to prove this is greater equal am plus 1, which is just bm plus 1 into m plus 1. So that is same as proving b1 plus b2 plus b3 up till bm is greater equal bm plus 1 into m. These are basically the same thing. Right?
Yeah.
Which is same as proving m plus 1 times b1 plus b2 up till bm is greater equal am plus 1 times m. Now, m plus 1 times
Can you
b.
please repeat this step? I actually got lost here.
Okay, so am plus 1 is basically bm plus, sorry, bm plus 1 is am plus 1 by m plus 1. So if you replace this term by am plus 1 by m plus 1, and then you take that to this side.
Okay, yeah, okay, got it.
We know b1 into m plus 1 plus b2 into m plus 1 up till bm into m plus 1 is same as b1 plus 2b2 plus 3b3 up till mbm plus b1 into m plus b2 into m minus 1 b3 into m minus 2 up till bm. b1 is same as a1, b2 2b2 is same as a2, 3b3 is same as a3. What we're left with is b1 into m, b2 into m minus 1, and so on. Is that okay? Hmm. I'll assume that's okay. So this is A1 plus A2 plus A3 till AM. Now, that can also be written as, let's just write this as I equals 1. B1 into 1. We can write this as B1 plus B1 plus B2 plus B1 plus B2 plus B3. B1 plus B2 plus B3. This form, you should try to remember translates to this. Like, okay, maybe not remember, but like, I hope one, it's clear why that's true. And two, like, just the intuition why you would do that. Is it okay for now? I'll assume it's fine. What can you say about B1, B1 plus B2, B1 plus B2 plus B3, and so on? You know, from our induction hypothesis that summation BI is greater equal AI for all k less than equal n. So we know B1 plus B2 plus B3 up till BI is less than equal AI for all n less than equal n. So this equation is less than equal summation AI. I goes from 1 to n plus A1 plus A2 plus A3 up till AM, which is just 2 times A1 plus A2 A3 up till AM. Is that fine?
Yeah, okay. Yeah, got it.
Now this can be written as A1 plus AM, A2 plus AM minus 1, by the statement given in the question. We know this is less than equal AM plus 1, another AM plus 1, another AM plus 1. Since there are m terms, it's AM plus 1 times m. We get m plus 1 into summation BI. I goes from 1 to m is less than equal m times AM plus 1, which is what we had to prove here. So we are done. I know it was like a proof on the longer side, but did everyone at least partially follow?
Yeah, I got it, but we could also do it the other way using simple induction. Could we?
Go on.
Like if we get a1 upon 1 plus a2 upon 2 up till ak upon k greater than equal to ak, that is what we have. So we could get uh, this whole summation plus ak1 ak plus 1 upon k plus 1, that must be greater than equal to ak plus 1. That is what we need to prove.
Yeah.
A into k plus 1. So we could just add it ak. So it will, the left hand side must be greater than ak plus 1 upon k plus 1. And if we solve it, then I guess we get it. We get
So-
the desired inequality.
So enough to prove is ak plus 1 by k plus 1 is greater equal ak plus 1. Is that what you're saying?
Yeah.
Which translates to ak plus 1 into k plus 1 is greater equal ak times k plus, sorry, k. No. ak times k plus 1 greater equal ak plus 1 times k. Now, this might not even be true, let alone like being true for every single k. Like, okay, let's think of this thing. A1 is 2. A2 is 3. Now, A2 into 3, let's say is that one. A3 into 2. If I put A3 as like 4, do we have a problem? I'm not sure. Let's see. A1 plus A2 is greater equal A3. Yeah, if A3 is 4, then this is not true. Although this sequence does work in the problem. Are you seeing why that doesn't? Like we haven't proved it. We haven't even proved this yet. Because it's not true. We actually cannot prove this. I don't think I explained it well, but do you see why that's incorrect? Or at least incomplete?
Yeah, I think using strong induction is more sharp.
Yeah, exactly. Like this inequality gets 2 loops. But yeah, it was a good attempt.
Here, isn't it 12 is greater than equal to 12? Isn't it satisfying?
It is. It is 3, sorry. 3 into 3 greater equal 4 into 2.
Oh, okay. So it is satisfying. No?
Wait, it is satisfying. Wait, let me find another example. Okay, A3 is 4.6. So this is 3 into 3 greater equal 4.6 into 2, which doesn't work. But 2 plus 3, which is A1 plus A2, is still greater equal A3, which is 4.6. I think that this is like a better example.
Okay. Getting it.
I think we are like over time for now, but you could definitely try these 2 questions. And I'll try to send like a problem set. Like it's not mandatory, but try to do the problem. So that Any questions?
For second one, can you give a hint because I was trying to homogenize, but I couldn't really do it.
Okay, a hint would be, since A, B, and C are like positive integers with product 1, you know C is 1 by A. And if you put A as X by Y, B as Y by Z, you get C as Z by X. Try to prove that you can put all numbers with product 1 in such a form, and then try to use the substitution for the problem.
Oh yeah, I heard the substitution is useful when ABC is equals to 1. Okay, thanks.
I had one question. Like when we are given such product conditions, ABC is equal to 1, is there any good way of proving that there is a bound on the sum of ABC? Because like by AMGM we only get that it is greater than 3, but anything for the upper bound?
There is no upper bound actually on A plus B plus
Ah,
C.
yes. Here it is not, but like A can be large. But is there any good way to get a bound on that if there are?
Well, like an upper bound on numbers with product 1 is really hard, because you can make one number extremely large and the rest numbers quite small, and you cannot possibly bound that. But in
Okay.
certain situations where you're given like the sum or some other equation that's equal to some constant, you can maybe find bounds, and that might just be your problem. But just ABC is 1. I don't think there's any nice upper bound. Any other questions regarding the class or not regarding the class? I'll assume that's a no.
I had one last question. Like this substitution that you showed us, is there some place where I can learn more of it?
Um, I am not sure. I will try to make a list of the substitutions I have seen before. And
Okay. Thank you.
yeah, I never did Vijay Venkateshwara sir's book for inequalities. What I did follow was the Secrets book, which I really like. And yeah, Evan Chen's handouts do mention some substitutions. Those are quite famous. um, Secrets and inequalities. I could probably link it or ask someone to link it. Okay, I'll just do it. Yeah, that one. I think it's available on AOPS somewhere. I have to find the thread. It's not like wait, that's not it. I'll probably have it linked in the OMC server. I can't find it for now. But that is a good book that I did for Olympiad.